This will be the last kind of integral we'll be learning to evaluate, and it's also the most difficult, but there is some good in this integral after all. So this integral is called integrals of rational functions from 0 to infinity. So notice that where our bounds before were negative infinity to infinity, now we're starting at 0, which is going to cause some complications. So before we look at the more difficult case, let's look at the easier case, where we have an even function. So pretend this integrand inside here is even, and remember, even means that if you plug in negative x into here, you get the same function back, and indeed that's true, because if you plug in negative x into negative x squared, you just get x squared. If you have negative x squared, again, you get x squared. Okay? So this from 0 to infinity. So think about an even function. An even function graphically is characterized how? So an even function graphically is characterized by the side on the left of the vertical y-axis being the same as the side on the right of the vertical y-axis. So if we're integrating from 0 to infinity, that means we're integrating all of this. But that's the same thing as integrating all of this, right? There's no difference. So if we want the integral from 0 to infinity, all we really have to do is take the integral from negative infinity to infinity, and then just divide by 2 if we just want that portion, right? So that's exactly what we do here. Since this function is even, I just take 1/2 of the integral from negative infinity to infinity of 1 over this denominator right here, dx. And now what is this? This is just the integral of a rational function, because this numerator and the denominator are both rational, from negative infinity to infinity. And we know how to do that. That's the very first type we did. So we just solve for this. We take 1/2 at the end, and we're done. But of course, we have also cases where the integrand will not be even. That's going to happen a lot more often. So we're going to assume it's not even. And so the general form we want to evaluate is integral from 0 to infinity, px over qx, rational, dx. Okay, so we're going to do it through example. We're going to try to solve this brown integral right here, integral from 0 to infinity, 1 over x cubed plus 1 dx. Let's confirm it's not even. If I plug in negative x into here, I get 1 over minus x cubed plus 1, which is not the same as this, of course. Okay, so the good news here is that we're going to be using the keyhole contour again, so we don't have to learn any new contours. So again, the keyhole contour starts at epsilon right here. It goes to r. It makes the full circle of radius r, comes back here, goes back the opposite direction back to epsilon, and then makes the circle of radius epsilon and comes back to its starting point. Okay, that's the keyhole contour. So now the weird thing about this kind of integral is that up until now, we've been using this function inside here as our main function. But in this kind of integral, we're going to be defining a new function. So our immediate goal right now is going to be try to find the integral around the keyhole contour of r of z natural log of z dz. So you might be thinking, why am I complicating things by adding a natural log into a rational function? Isn't that just going to cause things to get messy? Well, it's going to cause things to cancel out in the end, which we really like. So let's go ahead and do that. So natural log times my rational function is basically just going to be ln z over z cubed plus 1. Okay? So if I want to find the integral around the keyhole contour of that, that's going to be 4 integrals, right? Because it's the keyhole contour is split into 4 parts. First, from epsilon to r of natural log x over 1 plus x cubed dx. These are x because it's on the positive real axis, plus the integral around the big circle, and I put an asterisk, which means estimation, yeah, plus the integral back from r to epsilon. And now, again, note the nuance. So remember, what does natural log z equal? ln z equals natural log modulus z plus I theta, right? We said that in the previous video. So here, if I want ln z, when I come back around, my argument or my theta has changed. It has become 2 pi. And x is still x, so now I have natural log x plus I pi. 2 pi, okay? So when I have ln x plus 2 pi I, which is why I have to put ln x plus 2 pi here, instead of just putting ln x, okay? Divided by 1 plus x cubed. And the last integral is just the integral around the small circle, and we have to estimate that as well. So let's go ahead and do those estimations. So the green circle, the big circle estimation is given here. It's going to be less than or equal to the maximum value of z on the big circle of the modulus of the integrand times the 2 pi r, of course, because that's the length of the big circle circumference. So now we want to try to find the maximum value of this. So we're going to use a little bit different technique because we're dealing with natural logs here. So we take modulus this, and we split up this natural log z into its definition, so an ln modulus z plus I theta. And then we will split up the numerator and denominator into modulus, so this is less than or equal to. So what I did was I put a modulus on the numerator. And remember we talked about in a previous video how if you have 2 complex functions, or 2 complex numbers, let's say here is one complex number, and we have here's another complex number, and let's say you were to add their sum. So first you take their sum, so we have this, and we're adding it to this, so the sum is going to be something like this one right here, and then we take the modulus of that sum. Now, is that going to be less than or more than if we took the sum of the individual moduli? Well, it's going to be less than, because we see that by the triangle rule, these three form a triangle, and if we add these two sides, they're going to be greater than this side right here. Which simply, in algebraic terms, means that if we add this complex number plus this complex number modulus, it's going to be greater than or equal to the sum, and then we take the modulus. Okay, so we have modulus natural log modulus z, so we have two moduli here, but that'll be taken care of, plus modulus I theta over the modulus of the denominator. So natural log z is natural log modulus z is going to be what? So modulus z is r, because that's what we defined it as right here. So we have natural log r, still in modulus, plus theta, because theta is just a real number, right? And we know theta is positive because we said it goes from 0 to 2 pi. That's the range. So we can just take it straight out. This I goes away, and modulus I theta is just theta. And then, we have the denominator here. So now what do we do? So natural log r, think about that. So r is going to be a pretty big number, right? Eventually it's going to go to infinity, but we can just assume it's pretty big. So we can assume it's greater than or equal to 1. What is natural log of anything that's greater than or equal to 1? Let's draw a quick little graph of natural log. This is just for real numbers because r is real. So natural log looks like this, where this number right here is at 1. So if we have natural log of something less than 1, then yeah, it's going to be negative. But as long as it's greater than 1, we can assume r is something greater than 1. Then natural log will be positive. And when you take the modulus of a positive number, you don't really need the modulus at all. You just need the inside. So we have natural log r plus theta. And we're going to do that trick again where we take the denominator and we factor out a z cubed. So I have modulus z cubed. And after that's done, we are left with modulus 1 over z cubed plus 1. And of course, modulus z cubed is r cubed because modulus z is r. So we have natural log r plus theta over r cubed times this quantity. And as we did before, since we're just traveling on a circle, this quantity is, even though it looks complicated, really it's going to have some kind of maximum. So really what quantity we're looking at is 1 over this. So we're looking at that quantity right there. As we travel across our big circle, there's going to be some point where that's at a maximum. So we're just going to call that point 1 over c. Okay, so 1 over c is going to be our maximum. And so then we have natural log r plus theta over r cubed times c, so, or 1 over c really. And then what we have to do is multiply that by 2 pi r, and this r will cancel with this r, so we have r squared on the bottom. And now we ask ourselves, as r approaches infinity, what happens to this? Well, natural log r we can just look at the same graph. Here's a graph of natural log r, and if we were to draw a graph of r squared, what's that going to look like? That's just going to be a parabola, right? Now, which of these grows faster? Obviously, it's r squared. So since this grows so much faster than natural log r, as r approaches infinity, the denominator gets really, really, really big, and it just goes to 0. So that means that this integral goes to 0 as r approaches infinity. Okay, so the next thing we want to do is we want to try to find the purple integral around epsilon. So for this one, we have the integral here is less than or equal to maximum of z on the small circle of modulus natural log z over 1 plus z cubed times 2 pi epsilon. Okay, so again, we want to try to find the maximum value of this. We do the exact same calculations up until this point. Now we have modulus natural log epsilon plus theta over 1 plus z cubed modulus. So now let's note something. Let's draw that same graph of natural log. But notice that epsilon is really, really small, and we're going to take it to be really close to 0. So as we take it to be really close to 0, we see that the natural log of epsilon goes to negative infinity, which means it's getting really, really small. Well, it's getting really, really big in the negative direction. Okay, so if we take the natural log of something, and this inside the modulus is going to be negative, then if we want the modulus of that, you have to take that and make it negative, right? Because just as an example, let's say natural log epsilon was negative 100 at some point. Then if you want the modulus of negative 100, then you have to take negative 100. So we need negative natural log epsilon, which is why I wrote that here, plus theta over modulus 1 plus z cubed. And now, what happens here? So again, we have this 1 over modulus 1 plus z cubed, and this just has some value on the circle of radius epsilon that's the biggest, so we're just going to call that 1 over c. So that's written down here. And again, we have times 2 pi epsilon, because that's the circumference of the small circle. Now, this is more ambiguous. What does this approach as epsilon approaches 0? And the reason it's ambiguous is because as we approach epsilon 0 on natural log e, we get to negative infinity, or really we get to infinity, right? But as we approach 0 on epsilon, we get 0. So this approaches 0, but this approaches infinity, and infinity times 0 is an indeterminate form. So we need to use L'Hopital's rule on this one. So doing that, we would take the derivative of the top and the bottom I've made 1 over e, so that'll be the denominator. And I take the derivative of the top and bottom, and I get this expression, which cancels out to just epsilon. So now we take the limit as epsilon approaches 0 of epsilon, which is of course 0. So now we have a definition for it. It's going to be 0 as epsilon approaches 0. So we see that the good thing is both the green integral and the purple integral approach 0 as r approaches infinity and epsilon approaches 0, which is exactly what we wanted. Okay? So now let's see what happens. So that means the integral around the keyhole is just equal to the 2 remaining integrals. The integral from 0 to infinity of ln x over 1 plus x cubed dx. And what I had before, I had over here plus the integral from r to epsilon. I'm going to flip this. I'm going to make this a negative sign, so it's the integral from 0 to infinity. Okay? So minus the integral from 0 to infinity of natural log x plus 2 pi I over 1 plus x cubed dx. Now notice something. These integrals look almost the same, right? The only difference is that this has a ln x plus 2 pi I. But the good thing is, because of how integrals work, we can just kind of, we can take that out. So we have this integral right here, written word for word. And I've split this integral here into 2 parts. I've split it up into one part that has integrand ln x over 1 plus x cubed, and the other part has integrand 2 pi I over 1 plus x cubed. So I have this minus that. And the 2 pi I is a constant, so I took it out. Now the great thing, here's the magical step, where this cancels with this, because notice they're the same exact integral, and also notice that this is the only 2 integrals now that have the natural log, and now this last integral I'm left with has no trace of a natural log. So this weird part is that by introducing a natural log, I actually just take it out in the end, and it just serves its purpose so beautifully. So now what's left? So I have that, I'm left with the integral negative 2 pi I, integral 0 to infinity, 1 over 1 plus x cubed dx. And this integral right here in blue underline is what I'm looking for. So this equals that integral. And again, since this is equal to the keyhole contour integral in the end, it's going to be equal to, by residue theorem, 2 pi I times the sum of the residues of that original function. Don't forget, the function you're doing still has to be natural log, because that's what was written up here. All the isolated singularities that are inside of the keyhole contour, okay? And 2 pi I. So the nice thing is the 2 pi I cancel with the 2 pi I here, but don't forget there's still a negative sign here. So if I find the negative sum of the residues, because remember the negative sign will go over here, then I've found the value of this integral, which is exactly what I wanted. So the last thing to do is just find the sum of the residues. So I've done that here. So let me just walk you through a few of the initial steps. So residues are where denominator equals 0, and also we have a possible case where we can have a residue here for natural log z, because natural log z is defined everywhere except at z equals 0. But notice something, a little technicality about the keyhole contour. Z equals 0 would be right here, and that is not part of the keyhole contour, at least for this one. Now, as epsilon approaches 0, it's zeroing in on that origin, but really, since it's approaching 0, we never say epsilon is getting to 0. This 0 is never included in the keyhole contour, so we kind of work our way around that, and we don't need to worry about the isolated singularity for natural log z. So we just need to worry about when the denominator is 0. So 1 plus z cubed is equal to 0 when z equals minus 1, z equals e to the I pi over 3, or z equals e to the 5 pi over 3. E to the 5 pi I over 3. So for simplicity, we're going to call e to the pi I over 3 as z1. We're going to call e to the 5 pi I over 3 as z2. Okay? So if we want the first residue, we want the residue of the function at minus 1. Then we really want the residue of this function, and I'm going to split up the denominator so it's going to be more instructive into 3 parts. So since we have 3 roots, I can just split it up into z minus the first root, z minus second root, z minus third root, okay, by algebra. So, and then I want it at negative 1, right? So how I do that, this basically is just a game of picking the right numerator and denominator. So the right numerator in this case, I want to pick this as the numerator inside this purple, because when I plug in negative 1, that numerator is not going to become undefined or anything. And of course, the last part, z plus 1 is the denominator, because when I take the derivative, it will be fine. So I would do the same thing. I would do, you plug in negative 1 into the numerator, divided by you plug in negative 1 into the derivative of the denominator. The nice thing about this is the derivative of the denominator is 1 in every case, because it's just z plus something. So we just have to plug it into the numerator. So I did that here, and I come up with this nasty looking expression right here. So I do the residue of the next one, and I plug in, so now what's my numerator? So I want to find the residue at z1, right? So my numerator is going to be just these terms right here. So the terms, this term, this term, this term, not z minus z1, because that'll cause the numerator to be undefined. So I just plug my, my z1 right into there, and I get this expression right here. And I do the last one, and same deal. So what's my numerator here? It's going to be, since I'm doing it at z2, I don't want to include this z minus z2 in my numerator, so I'm just going to be including like that. So that's going to be my denominator right there. So then I just plug my z2 into there and I get this. And what you have a few choices now. You can work it by hand. I did work it by hand. It's possible, but it takes a while. You can plug it into a calculator. You can plug it online, whatever you want to do. But you get that the sum of these residues is equal to negative 2 pi over 3 rad 3. And remember, we don't want the sum of the residues. We want the negative sum of the residues. So all we have to do is just take a negative sign in front of there, and we get that the integral we want, finally, is equal to 2 pi over 3 rad 3. So even though this is a really long journey, it is instructive, and it's good to help you try to figure out more difficult kinds of integrals from what we did before.